Good afternoon, everyone. My name is Taeho Lee, and I'm majoring in environment engineering at Yeongnam University. Today, I'm going to present my research titled Optimizations of Low-Impact Development Design for Reducing Runoff and Suspended Solids Using SWMM. My presentation has four parts, which is Introduction, Methods, Results, and Conclusions. Let's begin with a bit of a background about our project. This research was conducted as part of a PBL2 project courses. Our team worked toward publishing a journal paper in the Korean Society on Water Environment Journal, and I was a co-first author. We also received an award from the Korean Society of Water and Wastewater on July 3rd for this work. Rapid urbanization has increased the impervious surfaces like asphalt and concrete, which prevents rainwater from soaking into the ground. As a result, cities face serious problems such as flooding, droughts, and water pollutions. To address these issues, LID has been widely applied in highly urbanized watersheds around the world. So, what is LID? It is a sustainable design strategy that helps cities restore their natural water cycle by letting more rainfall soak into the ground instead of flowing directly into the drains. And LID focuses on conserving local natural features and using small-scale systems such as infiltrations, filtrations, storage, evaporations, and detention. Simply put, LID makes the city behave more like a natural king. They reduce flooding and improve water quality. When LID is not installed, stormwater quickly flows into the drainage systems, causing flooding and pollutions. But even with LID, its performance varies greatly depending on its size, location, and type of its facilities. Also, since LED systems require high constructions and maintenance costs, therefore, before installing them in the real world, it is essential to model and predict their effects in advance. So that's why LED modeling plays such an important role in decision making design. For these simulations, we utilize the stormwater management models, SWMM, developed by the US EPA, which is Environment Protection Agency. It can simulate both runoff quantity and pollution quality during rainfall events in the urban areas. So I'm going to explain how we analyze the effects of LID. So our study site is in the Jungbang District, Gyeongsan City, Korea, and we evaluated the performance by analyzing the inflow concentrations at this red point, which is outflow. And we applied five different LID techniques, such as green roofs, permeable pavement, and bioretention, rain barrier, and vegetation swells. And then we applied 16 different LID scenarios with different LID combinations and LID size to analyze the runoff and suspended solids reduction. From now on, I'm going to show the results of our project. From A to D, figure A to D shows the runoff for each LID scenarios, and figure E to H present the corresponding suspended solids concentrations under the same conditions. The result shows that the both runoff and suspended solids decreased as the LID areas increased. In this slide, we examine the runoff rate and the reduction rates of runoff and suspended solids for each LID scenarios. On the left graph, the black line represents the scenarios with the greatest runoff reductions effect across all areas, which had a rain barrier by retention and vegetation swells combination in the subcatchment and porous pavement and vegetation swells in the rows of catchment. The next best were the blue, red, and the green combinations in that order. On the right side, we can see the two charts, which A shows the runoff reductions and the B shows the suspended solids reduction. The color order of the effectiveness was the green, blue, orange, and the purple, meaning those combinations achieved the most significant pollutant and runoff control overall. Here, I analyzed two indicators in the upper side, A to C, total pollutant loads, and the lower side, D to F, means peak pollutant loads. Total load means the overall amount of pollutants washed off during the entire rainfall period, while peak loads mean the maximum concentration released at a single moment, usually at the beginning of the heavy rain known as the first flush. As you can see, July showed the highest values because it had the heaviest rainfall, which washed away more pollutants from the roads and the surfaces. As we can see in the both upper and the lower graphs, the most significant reduction was observed when the LID area radio increased from 20 to 15. Next, I compared the costs and performance using the life cycle cost method. For instance, as I mentioned in the previous page, the porous pavement and vegetation swells combination reduces by about the 41.4%, while vegetation swells alone reduces it by the 30.2%. Although porous pavement and vegetation swells achieved a higher reduction rate, it was much more expensive in terms of the life cycle cost, as you can see in this page. So instead of just minimizing the cost, we should find a balance between the cost and performance, such as maximizing the reduction per unit. To summarize, even with the same LID area, the runoff reduction varied greatly while the suspended solids reduction was more consistent. And third, overall, the porous pavement and vegetation swells combination exhibited about 3% higher runoff reductions than only applying the vegetation swells in the roads of catchments in every scenarios. And last, although porous pavement and vegetation swells increased cost by around 0.40 million US dollars over 20 years, but it delivered better runoff reduction performance. Uh, the findings are expected to provide essential data for establishing the future urban plan and water cycle management guidelines, helping policymakers prioritize LID projects that achieve the greatest benefits under limited budgets. Thank you for listening.